Then good afternoon, everyone. Welcome to the first lecture on the course on Python-based introduction to mathematical proofs. Our speaker for this course is Professor Zurab Janelidze, and let me pin him down so that you can see him. Yeah, so Professor Janelidze is professor of mathematics at the University of Stellenbosch, and some of you might have already met him in some of our NITheP activities. He already offered us a very interesting mini school on a gentle introduction to category theory and its applications, and recently he also presented at the NITheP colloquium on a similar topic. Yeah? And today he very kindly agreed, although he's a very busy person because he's also the president of the South African Mathematical Society this year, to offer a course on how to prove mathematical theorems or statements using Python. Yeah? And this is probably a very interesting topic that fits perfectly well with our summer school, because all of you just learned Python the first 2 weeks of February, and now you will be given the opportunity to apply it to a mathematical framework. Zurab, without further ado, people are here to listen to you, not to listen to me. You're most and welcome to, I don't know if you're planning to share your screen or whatever technology you're planning to use, and over to you. And please, again, as I said this morning, we are using the meeting format of Zoom, so you're welcome to ask your questions anytime. You just need to unmute yourself, maybe just wait for the opportunity where the presentation allows, or make use of the chat facility at the bottom. I will keep an eye on it, and then maybe we can ask you to unmute yourselves. Yeah. Perfect. And I see that, yes, and Benjamin asked us to give us a first sign of life, to tell us where you're zooming in from. Yeah, that's always quite nice to know. And I see there's still people in the waiting room. Okay, Zurab, please.
I will do that. Thank you very much, Francesco. So this session is being recorded, right?
Yes, and we will post it on our special YouTube channel as soon as possible after your lecture.
Thank you. So I wanted to also kind of emphasize that, because on one hand, of course, everybody is welcome to ask questions and interact, but if for some reason you're not comfortable under the recorded setting and you don't want to do that, that's fine as well. Of course, you can then engage outside that session, either through the Slack, or there is also WhatsApp, or maybe at the end, once we stop the recording, we can still stay on for a few more minutes to take those kinds of questions for anyone who might not want to be on the recording. But otherwise, it will be nice if you can interrupt and ask questions as we go on. I want to begin with a bit of kind of background context, the foundation on which we're going to try to build. So I realize that you might, through your university studies or maybe other encounters with mathematics, you might have felt that the proofs is where you don't find particular interest, or maybe it could even be a weak point. And in some sense, this Python-based proof system that we designed at Stellenbosch, and let me then take this opportunity to say that I'm talking to you from Stellenbosch. I'm not physically on the campus of Stellenbosch University, I'm at home, but my home also is in Stellenbosch. So this system that we designed at Stellenbosch, the idea was to open doors to mathematical proofs to those people who might not have been very comfortable with mathematical proofs at the time of their studies, but also to reinforce those who are comfortable, to reinforce them with a tool that could be useful. In general, the idea for having computer software assisting you with proofs is not a new idea, of course. There are lots of proof assistants around the world. But we try to develop something that's user-friendly and something that you can learn quickly without having to go through many, many pages of documentation in terms of learning the language of how to use the software before you can start making effective use of it. At the same time, the system we're going to use is very much in its infancy. So it has very primitive functionality at this point. But we hope that along the next few years, we will be able to advance the system and bring it up to the level of other proof assistants that exist. Okay, so that's like a very general background. Now, a bit more specific, this course will try to show you that if you don't particularly like mathematical proofs, but you like programming a lot, I will try to show you that you can think of writing down a mathematical proof as an instance of writing down a computer program. So we can actually, I mean, this is real. This is not some kind of magic that only works in like a restricted context. You can turn all of the mathematical formal language into an instance of a computer program, but you can also do it the other way around. You can also think of computer programming as an instance of doing mathematics. And historically, that's how it happened. We first had mathematics and then we had computers. And of course, mathematics had made a huge input into developing the idea of a computer and the structuring programming languages, which are very much based on the structure of mathematical logic and so on. But today we're not taking the historical route. Today we are taking kind of the other way around, where we assume that that computer programming is something that's natural for us, and we want to use that as a tool for understanding how mathematical proofs are structured. Okay, so this is like the second layer of the background. And now I want to move down to the third layer and say a few words about what is a mathematical proof. Before I do that, I need to go back to some logistics. So the notes that you're seeing on my screen are from my blog. We can also put these notes on the Moodle page, but I think that my blog is also quite easily accessible. These notes form a kind of background to our interaction. There are activities in these notes, and so most of these activities we will do together during these live sessions, but some of them you will be required to do on your own, and that you can do through the activities posted on the Moodle platform, where they have a structure of a quiz which you need to complete by a certain day and so on. All the deadlines are not so strict deadlines, so we have due dates, but if you complete something later, we will be aware that you completed it later, but it's okay still, especially if Python is new for you. I was informed that some part of the group are being introduced to Python for the first time. And so if you not feel comfortable completing these activities because of that reason, that's fine, you can submit them later. But I would still encourage you to try, because we don't really use that sophisticated part of Python. So if you understood like very, very basics, then you should be fine. Okay, let's go back a little bit to mathematics, and then we'll say something about setting up this proof system. So a typical mathematics lecture, which explains what the purpose of mathematical proof is, would tell you that mathematical proofs are there to verify that something is indeed correct. Now, of course, that's true, but I very much don't like that as the primary motivation, because it takes away a very important piece of reality. Namely that, I mean, it kind of gives you the impression that we come up with wonderful ideas, and then we just experiment and test them if they're right or not. And that's what mathematical proof does. But I guess just as much as this is so in physics, where you can think of experimentation as a means of confirming ideas. Performing experiments in physics also is a means of coming up with new ideas. Am I saying something that makes sense, Francesco? Is it true that experiments often lead us to new ideas which we didn't think of on the theory side?
Yeah, definitely. Thank you, Zurab. That's perfect.
So mathematical proofs are very much like that. So on one hand, you can think of proofs as a tool for confirming your mathematical ideas, but at the same time, and maybe even more than in physics, it is a tool for arriving to new mathematical insights, like completely new insights, which you would have never arrived to just with your intuition, without going through the path of trying to prove something. And very often you construct a proof without even knowing in the beginning what you're going to be proving. And that kind of exploratory approach in mathematical research is responsible for a lot of discoveries in mathematics, which later have had also very important applications. So the way I motivate and explain what a mathematical proof is by these 3 bullet points, where I put on the first position discovery of new mathematical knowledge, and then on the second position analyzing existing mathematical knowledge. You might not just want to confirm something, you might also want to understand why something is so and so. So by looking at the subtleties, you might get some ideas as well. And then the most kind of practical aspect of it is indeed to verify truthfulness of a piece of mathematical knowledge. What we're going to do in our course is through some activities that involve coding in Python, we're going to get a flavor of the world that's provided to us by mathematical proofs. So by completing this course, you will have a kind of basic intuitive idea of what is the foundations of proofs, what is it like to prove something, and how do you actually go about structuring your proof in such a way that it serves the third purpose. How can we be so certain that when we have a mathematical proof, the knowledge is really being confirmed, and there is no doubt that about truthfulness of that piece of knowledge. Okay, so let's now go to a practical side. I'm going to share my screen with the Moodle page, or maybe that's not necessary. I actually want to ask a question whether everyone was able to download the Sophia.py module for Python and possibly even test it out a little bit. So I'm going to share my Spider interface for Python, and then we go from there. So I found that this Spider interface is the most convenient, but you might have other ones you prefer. I guess in the first 2 weeks, you already got introduced to various platforms. And what you should have, the setup you should have is this Sophia.py file, which can be downloaded from Moodle page as well as GitHub linked to that Moodle page. And then also you might want to create a separate file, let's say called example.py, where you'll be writing out your test code. So if anyone does not have this setup already and would like to get some hints on how to get there, you're welcome to ask corresponding questions now.
Hi, Doctor. Prof.
Yes, hello.
Can I use any IDE, or is it you want us to use Spider?
You can use any.
Okay, cool.
I see
Thanks.
there is a note from Benjamin that Spider is taught in the Python course. Well, Benjamin, this is how I learned about Spider. I learned it from your course. I had some other interface, but then when I looked at your videos, I saw the Spider and I downloaded it. I checked, it actually works much better than any other I knew before. So thank you very much for that. Sophia cannot be done as a pip install, unfortunately, but you don't really need to install it. So all you need to do is to have that file sophia.py and then put it in the folder, which is your runtime folder. Okay, so there is a request to take you through forgetting Sophia. So let's do that then. So in that case, I'm going to switch to the Moodle page. So on the Moodle page, you will see under so week 2 Python, that's still from last week, and then there is the next section there called week 3 content for Python-based introduction to mathematical proofs. Then you have there the link for the lecture notes. That's where we were before. If you click on this link, you will be able to see these lecture notes. Then there is a support group. So it's good to use the Slack. But before I knew that we could use Slack, I also set up a WhatsApp group. So if you want to ask questions through that WhatsApp group, you're also welcome to do that. So there's the Slack group, and there is also a WhatsApp group, which you can get the link from here. Then there is a link to this live session. And finally, we have here, well, not finally, but the next thing here is a Math 14 Feb assignment. So this is your first assignment due today, where you will check if you can run Sophia or not. So if we go into this assignment, you'll see that there is this file called sophia.py. And what you want to do is to download this file. So you can click on it, then it will download in your system. And then you want to copy this file and move to the directory which is your runtime directory for Python. And if you're not sure how to find your runtime directory for Python, then I must ask for help from Benjamin to say a few words about that. So is everybody fine with finding your runtime directory for Python? Okay, there is at least one person. Okay, more than one person. So in Spider, on the file, I'm reading Benjamin's instructions. Benjamin, would you like to turn on your microphone if you can? Maybe it's useful if you guide them through this part.
No, it's fine. Prof, do you want to share your screen of Spider?
Yeah, I will do that.
I think also the runtime directory is a confusing term for people that might not know. It's just a directory where your Python file is going to be running from.
So I'm sharing the screen. What should we do here?
So on the far right, you can click on that. So that's currently your directory where files are running. So if you just click on the folder on the far right, on the folder symbol, yeah.
Okay, and that's how you browse the directory, right?
Yeah, so that's how I browse your directory. And if you go below that, where it says Variable Explorer, if you go to the next tab, a little bit down, with your mouse down. See, but plots within files. So click on files.
Right.
So this shows you your current working directory where everything's inside.
Okay, so in case you have Spider, then it's easy to discover the address to that directory. And what you want to do is to copy paste sophia.py there. But it's not, I don't think it's showing that directory. I'm not sure, but yeah. So please try that and let's see if it works.
So Prof, can you just go to, if you click on folder and go to D Python Sophia, so just go to your D folder and just click on the icon.
How did you know that it's there?
I can see on the far left, your far left, it's D Python.
Right. Yes.
the way I can see the location. So there we go.
That's right, yeah. But this is, I think this is my runtime directory, no? Not
Yes,
the other one.
that's it, yeah.
But now how can they find theirs? Because it wasn't showing, what was showing here wasn't the right one before, right?
Well, you can choose where you want your runtime directory to be. So previously it was the previous location you showed first. So
Oh,
just
I
click
see.
on that folder. Click on that folder, and that's where it currently is. So you can choose where your runtime directory is, or directory where your
Evander is
files are.
asking if we're showing anything other than the Moodle screen. Yes, we are. I've switched my screens now. I'm not sharing the Moodle screen anymore. Now I'm sharing the Spider screen. And
Yes,
if you're
I
not
can see the
seeing
Spider
it, most
screen, yeah.
likely there is a connection issue.
No, that's what we see. We can see the spider screen and so
Yeah, but I think some participants cannot see it yet.
maybe it takes a while to upload.
Yes, Francois, even if it's in a virtual environment, that does make a difference. You still can access your files if it's in your C or D drive. Even if you're running Linux as well, you can access it in any way.
Okay, so let's see if there are still some participants who are struggling to put sophia.py in the right place. So was this not covered, the directory in the first 2 weeks?
We did cover it when we read like CSV files. We did cover how to.
So what's the right term? If I'm using the wrong term, what should I be using?
No, you use the correct term, Prof. I just said the directory where your files are located, just to kind of simplify it. But runtime is exactly correct.
So can you repeat that last part, because I think it was too silent and I couldn't hear it.
No, runtime directory is a correct term. I just said, just try to make it simple and say where the files are run from.
Where the files are run from. Okay. Thanks. Okay. Is there still anyone who is not able to locate the place where their files are run from?
So maybe let me ask this question differently. Can we safely say in layman terms, it is where the program is running, or where all my Python programs are running?
Yeah.
Yes.
Okay, cool.
And so that's where you need to move the file called sophia.py.
Okay, all right, cool.
So you can kind of try to do that as I'm going to be speaking. We're not going to use Python immediately. So let me continue with a bit of general explanations, and then I hope that by that time you will have that file copied there. Okay, so I want to now go back to my other screen. Maybe I should share the entire screen so that it's not difficult to switch between. So now all of my desktop should be visible, and I might want to move some things around here. So here we have the lecture notes. Yeah, so the first activity was to do this, namely to copy the file sophia.py in that thing we are calling runtime directory. And then what you need to do is to open a new file, which you can call anything.py. And after that, copy paste this code there and then run it. And once you run it, something will show, namely this thing will show. And what you want to do with this thing is just to take a picture of it and upload it in here. So you see we already have 5 submissions. If I go here, I can see 5 submissions. And for instance, this. And when I open this picture, it shows me how your picture should look like. So this person is using Jupyter for the Python system. And if you don't know how to take a picture of your desktop or a part of your desktop, then that's something you might want to figure out later today. You can search on Google how to do that. There are various software for doing this, and it might also be embedded in your operating system. Or you can just use your phone as well. No, so Sophia is not included by default in anything. Sophia is a module that's developed, it's being developed at Stellenbosch University. It's a new piece of software. It hasn't been published yet. I mean, it is available online for free, but we haven't integrated yet in any other system. Eric says that you couldn't find the file. The file is available for download from either Moodle. So if we go back here, you can go into this activity, Math 14 Feb assignment, and then you have the file here. Or you can go to this link on GitHub and download it from there. But it's easier to download it from Moodle. Okay. Now let's go back a bit on the theory side, and meanwhile you can try maybe to set Sophia up on your side. So we will work in 3 language layers. Something we will call intuitive layer. This is the ordinary language. This is where we exchange our ideas. This language is not a precise language. It's not as precise as the mathematical language, but that's the whole point of it. By being less precise, we are able to express things with a bit less certainty, but that's the best you can do when you have a new idea. So new ideas arrive to us in a less precise form, and then we try to make them precise. And so the process of making ideas precise takes us from intuitive layer to formal layer, where we try to express our ideas using certain mathematical formulas. And then we have the 3rd layer, the computational layer, where we use the rules of mathematics to verify whether our ideas are correct or not. And this 3rd layer is the one for which we will use Sophia. So it's the Python program that allows us to express our mathematical formulas in such a way that it at the same time confirms the validity of what we're trying to establish. Okay. There are a few concepts to begin with, and these concepts basically refer to the formal layer. So first we need to explain the language in which we're going to formalize things. There is ordinary mathematical language, of course, which we are used to through various mathematics courses, but that language that we're used to is not precise enough at the computational level when we want to implement everything on the computer. I mean, you know how precise a programming language is, where every single character matters, right? And so we want to now have a way of kind of rewriting mathematical ideas from the formal mathematical language to a computational mathematical language where things are so precise that even computer will be able to verify things for us. So we need to develop a kind of extension of the usual mathematical language which will take care of this computational side. And for that, I mean, we need to do that slowly, step by step, so that we have a good understanding of that language. So the language we're going to work with is a specific language that's designed for this Sophia software. The language is also called Sophia. Actually, it's the language that's called Sophia, and based on that, we have the software. It's the kind of language which requires least amount of kind of introduction. If you look at other formal languages in mathematics, it takes quite a while to understand how they work. Sophia is supposed to be the most intuitive language in that sense, but there is still a bit of work to do, even though it is most intuitive. So the first thing to keep in mind is that anything that's a valid formula in the Sophia language, we will have a specific term to refer to it. We will call it an expression. At this point, I want to open my Blackboard and explain these things on example. So let's say we want to write down that 1 plus 1 equals to 2. In ordinary mathematical language, this is very good. 1 plus 1 equals 2. Everybody understands what this means. Now, in Sophia, because Sophia in the beginning doesn't know any mathematics, right? The idea is that she will be learning mathematics together with us. So Sophia will wonder at this expression in several different ways. For example, she will not be sure whether we read this way, where we first add 1 with itself and then equate that thing to 2, or whether maybe we want to add to 1 the fact that 1 equals to 2. So there are 2 interpretations for 1 plus 1 equals to 2. One is this, and the other one is the other one. So we have to specify where the brackets go. And now let me ask the audience, which one do you think is correct? Option A or option B?
B.
Option B.
I agree, yes. So to do that, we're going to add brackets in. The bracket will go here. Now, in Sophia, part of the flexibility of Sophia is that we can really start writing things down without Sophia knowing in advance what we mean by them. And as such, we still need to tell Sophia that we don't want to think of equals to as a separate statement. Like imagine instead of this, I had 1 plus 1 is a number. So here is a number goes together, right? But in the previous example, equals to does not go together. Equals is separate and 2 plays a similar role as 1 plus 1 does. So we're equating 2 things. So that's why we want to have a pair of brackets there as well, around 2. Now, because we have a pair of brackets around 2, we also want brackets around 1. Why is that? Otherwise, if we don't, then Sophia will not be able to distinguish this as a separate entity. She will think that this whole thing has its own meaning, where it's impossible to extract this as a separate independent part of it. Just like with this expression is a number, you don't really want to think of So if I write separately, right? This could be an interjection, right? Right? But this has nothing to do with is a number, even though U and M appear part of the word. So you see the level at which we have to be precise in communicating our mathematical formulas to Sophia. So this will now be a more valid expression for 1 plus 1 equals to 2. So such a thing is called an expression in Sophia. And there is only one rule that defines an expression. The rule is that the brackets should be placed correctly. So the square brackets have a specific meaning, and whenever a bracket is opened up, it should close at some point. So for example, you cannot have something like this, or something like this, where you've got 2 open brackets and they never close. This is not an expression. You see, we are using.
Zurab, sorry for disturbing.
Yes, please.
I see that Isaac is raising his hand. Maybe Isaac, if you want to quickly ask your question to Zurab, if it helps for the general understanding.
Yes, please.
Okay, thanks. I would like to know, writing the expressions, will you have to be consistent with the brackets? For instance, the one on the left-hand side, we have the square bracket. On the right-hand side, what happens if you use a parenthesis? So I just want to know if you have to be consistent with the bracket, or as long as it's a bracket, Sophia understands.
You have to be consistent with them. You always have to use square brackets. If you go back to Sophia module, the fact that you have to use square brackets is indicated here. So this is the left bracket and this is the right bracket. If you don't like square brackets, you can change these characters here in Sophia module, and then you'll be able to use other types of brackets instead of square instead of square brackets. But at the moment, the way Sophia module is written up, she will only recognize something to be a bracket in the Sophia sense if it's a square bracket. So if you open up a square bracket, it has to close with a square bracket. Does that answer your question?
Yes, please. Thanks.
Thank you. I want to emphasize that the word expression is now going to mean something very specific for us. So it's no longer a vague word which could mean various different things. Expression is very specifically a sequence of characters where there is a square bracketing done, or maybe not done. That's still fine. If there are no square brackets, it's still a Sophia expression. The only rule is that every open bracket should have a corresponding closing bracket. And this is actually a very nice mathematical description, how to figure out whether this rule is satisfied or not. And the algorithm that can make you figure this out is very simple. You simply count how many open brackets you have. So you read your string from left to right, and you count how many open brackets you have and how many closed ones you have. At each point in time, the number of your open brackets should always be bigger or equal to the number of your closed brackets. And by the time you reach the end, the numbers must be equal. So if that holds, then you will have an expression. And we can I can explain this one more time on an example. So I'm reading now. Let's actually go back to this. I'm reading now this expression, and so I'm counting the open and closed brackets. So I've got one open bracket and 0 closed brackets. So 1 is bigger than 0, so I'm fine. Then 1 open bracket, well, actually 2 open brackets and 0 closed brackets. Then I have 2 open brackets and 1 closed bracket. So 2 is still bigger than 1, so that's good. Then I have 3 open brackets and 1 closed bracket, 3 open brackets and 2 closed brackets, 3 open brackets and 3 closed brackets. It's still good, they're equal. The left one should be bigger or equal. Then I have 4 open brackets and 3 closed brackets, still good. And then finally I have 4 open and 4 closed brackets. So it's a Sophia expression. So you see, you can also use this algorithm to write yourself a Python code that checks whether a string is a Sophia expression or not. But you don't have to necessarily do that because this function is already implemented in Sophia module. And let me demonstrate that to you. Okay, I think I got myself lost here a bit with files. This is where we are. So it's this code here. I'm going to copy this and paste it right here. And then run it. Let me explain what this program does. Well, first of all, the first line, this loads the Sophia module. If you don't include this line, then none of the Sophia commands will be accessible to your Python code. What the second line does is it introduces a new object, which is called a proposition. So a proposition is something which contains some mathematical formula. So in other words, a mathematical expression. It could be something we will prove later, or it could be something we will adopt as one of the initial assumptions. So such a thing will then be called axiom. We will come back to proofs and axioms and also theorems later on. Then we introduce a string here, e, and we call this function valexp with an underscore that's accessible once I have a proposition object right here. So p dot val x calls a function that decides whether E is a valid expression or not. It will return a Boolean value, and then the Boolean value will be turned into string and attached to this phrase saying E is a valid Sophia expression equals. So if you look at the output, it says expression is a valid Sophia expression equals true. So the first part, the first word here, expression, comes from the input we gave here. We assign that value to E, and now we are told that this is indeed a valid Sophia expression because it evaluates to true. If I want to make it to be an invalid expression or not a Sophia expression, I can put one open bracket, which I don't close. And then when I run this, you see now it tells me that this thing, being a valid Sophia expression, is false. So you can use this little code to test out whether something is a valid Sophia expression or not. And those of you who already have your Sophia module installed and everything, you might want to run this code and experiment with it. Otherwise, there is a Moodle activity on this as well. It's actually a quiz, which will, okay, sorry, I take this back, because before you complete, now what I'm going to say applies to not just this quiz, but all the other quizzes. Before you complete a quiz, you want to make sure you master well the topic on which the quiz is. This specific quiz is on identifying expressions and things called statements and formulas, which we're going to explain in a moment. And so you first want to master these before you take this quiz, but you can master those by playing with this code, or maybe going through the video recording of this lecture and listening carefully how I define what a Sophia expression is. Okay, so at this point, I want to kind of ask a question to the audience just to make sure that they have the right understanding of what an expression is. 1 plus 1 equals 3. Is this a valid Sophia expression? So please post your answer in the chat. Is 1 plus 1 equal 3 a valid Sophia expression? So someone says no. Someone says yes. But most of the participants say no. Okay, so thank you very much for your participation here. Now, when I write 1 plus 1 equals 3, of course, 1 plus 1 isn't equal to 3, right? So I'm not asking whether 1 plus 1 equals 3 is true or false. I'm asking if grammatically this sentence makes sense. And grammatically, for it to make sense, it just means that the brackets are placed correctly. Even though there are no brackets here, they're still placed correctly. But if there were brackets, for instance, if I put brackets there, or maybe I put brackets also around them, this will still remain to be an expression, a valid expression. So even if there are brackets, and even if 1 plus 1 isn't equal to 3, this is still a valid Sophia expression. Let's, I mean, it no longer, okay, so it no longer, remember before we said that we want to write this like that, right? That's what we said before, yes? But, okay, so this is how we would write if we want to say 1 plus 1 equals 3. This, Sophia will not recognize as 1 plus 1 being equal to 3. She will just recognize as some sequence of characters without any meaning attached to them. But it's still a valid expression. So it doesn't mean the same thing as what we might want it to mean, but it's still a valid expression. Having empty brackets is no problem, answering Tembelinen. Tembelihem. Okay, let's look at another question. So how about this one? Is this a valid Sophia expression? 1 plus 1 equals 3 is an expression indeed. So Evander, 1 plus 1 equals 3 is a valid Sophia expression. But it no longer means 1 + 1 = 3. It's just a sequence of characters which Sophia will have no idea what you mean by that. Okay, now I see that everyone is answering correctly. So this thing is a valid Sophia expression, even though there are no characters apart from brackets. It's still a valid expression because the brackets are placed correctly. What about this one? Is this a valid Sophia expression? That's right, it's not. It's quite obvious that the brackets are not placed correctly, but we can also test it by applying our algorithm. There is 1 open bracket and 0 closed, 2 open, 0 closed, 3 open, 0 closed, 3 open, 1 closed, 4 open, 1 closed, 4 open, 2 closed. I want at the end the open and the closed brackets to match, and they don't. So it's not a valid Sophia expression. Exactly. So validity of a Sophia expression does not have to correspond to mathematical truth. So it is okay in mathematics to write this. In formal mathematics, it's okay to write this. It doesn't mean that you're claiming it's true. Now in Sophia, we will be differentiating when we are claiming something to be true and when we're just considering an idea without such a claim. There will be a difference between these two things. And the difference between these two things is given by two different types of Sophia expressions, which will be called formulas and statements. So let's move to that topic now. So that's our next topic, statements and formulas. First, I'm going to define what they are, and then we're going to discuss the intuition. And as I said before, the intuition will be linked to whether I want to claim something to be true or whether I just want to consider an idea without being judged that maybe what I'm saying is not true. Okay. All Sophia expressions split into two groups. Just want to make my screen a bit bigger. So all Sophia expressions split into two groups, into statements and formulas. Statements will be the things that I will be claiming to be true, and formulas are just ideas which don't have to be true. I can still write them down. And the rules that define these are the following. So statements essentially are Sophia expressions that look like this: open bracket, close bracket, and something in between, whatever you like, as long as what you have inside is another expression. So this must be expression. Then another open bracket, close bracket. Again, this must be an expression inside there. And then you can have many of these. All statements look like this, except that it must also be not empty. So if you look at this definition, it says that a statement is a Sophia expression that has this form, but I forgot to add there the clause that it must be non-empty. We can test this out in this code, which checks whether something is a statement or not. So let me go back now to the spider. I really love this spider, and I'm so grateful to the course last couple of weeks, which taught me about it. So I'm going to enter here empty string. E will be empty string, as you see. I just put quotation mark with nothing inside. And then I'm going to run it. Something happened there. So you see, it tells me that the empty string, being a valid Sophia statement, is false. So the empty string is not allowed to be a statement. So you need to have at least one piece like this in a statement. You could have just one piece like that. So you could basically have something with an open bracket, close bracket, and some other expression in between. Or you could have several of such pieces, but you can't have 0 of them. So these are statements. Everything else are formulas. An example of a formula would be, for instance, this. Why is this a formula and not a statement? Well, if it were a statement, it should be obtained by putting these kinds of pieces together. I will not be able to do this here because, well, I see one piece like that, but then the thing next to it does not begin and end with an open bracket, with bracket. Another example of a formula would be the thing we had before. So this is a formula. Why? Because I've got this piece there, I've got that piece there, but then in between I have equality sign, which is not enclosed in brackets. Here in a statement, I can't have that. These two different yellow blocks cannot have anything in between them. So these are two examples of formulas. And if you know how to code with if-then clauses in Sophia, you should be able to write a program that determines whether something is a Sophia formula or not. Basically, your program will be a combination of the previous two programs where you first check it's an expression, and then you check if it's a statement, and if it's not a statement, then it must be a formula. Because as I said before, expressions split up exactly into these two classes. So something is either a Sophia expression must be either a statement or a formula. So if it's not a statement, then it has to be a formula. Okay. Let's see if this concept has been understood. Is this Sophia expression a statement or a formula? What do you think? Is it a statement? You can write S in chat if you think it's a statement, or is it a formula? You can write F if you think it's a formula. I see that most of you are writing S because you might be thinking, saying that today is a great day is kind of making a statement, right? And in Stellenbosch, it happens to be a great day today, so I would be eligible to make this statement. But for Sophia, if I have something like this that doesn't have any brackets, it will not be yet making the claim. It will be just considering the idea of there being a great day. And I would be eligible to say this along with this without me being prosecuted for it. So in ordinary conversation, if I made these two statements, today is a great day, and then next to it I said, today is raining and I'm sad, then the person I'm conversing with would tell me, that doesn't make sense. Then if it's raining and you're sad, why would you say it's a great day, right? But I still want to be allowed to think about things, even if maybe they're in contradiction with each other. So this is my intuitive state where I don't yet want to confirm everything. I want to experiment with thoughts and then maybe select some ideas and they will give me new ideas and so on. I want to have that intuitive freedom, even in formal mathematical language. And I do that through formulas, okay? When I want to claim that it's a great day today, the thing needs to be a statement in the sense of this definition, where the sentence needs to be constructed with blocks of bracketed expressions like this. And if you look at this thing, if you look at this whole thing, you cannot get this thing by placing some text, some expressions in brackets and combining them together. Why? Because there are no brackets at all. So this is an example of a Sophia expression which is not a statement. It's a formula. Does that make sense? Why is it a Sophia expression? Well, because it doesn't have any brackets. We already said if there are no brackets, then it means the brackets are correctly placed. So that part is fine. If I want to claim that today really is a great day, then the way I will do that is to turn it into Sophia statement, which means I would want to introduce these blocks. So for example, I could do it like this. Today is a great day. And then I put brackets around it. Now, when I speak to Sophia, and remember, Sophia is just kind of AI, if you like, but it's a very primitive type of AI. It doesn't really do much. The code is just 1,000 lines. So if I will tell Sophia today is a great day in this way, by not putting any brackets, then Sophia will not conclude that it must be a great day today. The only thing she will conclude is that I'm considering in my thought this idea of there being a great day. She will not know whether I'm convinced or not that it's actually a great day. So that's the role of formulas, okay? And if you think about it, also in real life, very often we write down formulas which are not right from the start necessarily correct. Then we need to maybe put some extra conditions and explain the meaning of the formula for it to actually become correct. We want to be able to write down formulas without worrying about its correctness in the first stage. And that's done through the things that are not statements. But now if I want to tell Sophia, I'm claiming today is a great day, then I have to put my expression in this format, where the format is that the whole thing should be constructed as a concatenation of these blocks, which were yellow before, now they're blue, where each block consists of opening bracket, close bracket, and some other expression inside. So let me ask another question. Is this a statement or a formula? Once again, write S or F. S for a statement, F for a formula. Great. So we've got this one block, open bracket, close bracket. So it's a statement. Fantastic. What about the one we had before? Is this a statement or a formula? So the other one was a statement. A statement or a formula? Everybody is saying a formula. Yes, exactly. Why? Because as we explained before, we do have these blocks, but then there is also something in between which there shouldn't be. Okay, great. So we're sorted with that. In this text here, the intuition behind formulas and statements are explained, which we already did. And some examples of that are given. For instance, there is one example about the alien. So we have here a statement because we have this open close bracket block, right? Now, let me actually draw this here. So if I were to write this, if I were to tell this to Sophia versus if I tell this to her. In the first case, well, let's begin with the second. In the second case, I'm just considering the concept of alien. Now, everybody agrees that the concept of alien exists, even if we're not quite sure whether actual aliens exist or not, right? So nobody has, well, maybe some people claim they have seen, but they haven't convinced me at least that aliens exist. And so we actually don't know whether aliens exist or not, right? But nevertheless, we have that concept in our language, yeah? So it's an example of some idea which we can't claim to be a valid idea, but it's still a valid idea in the sense that it's an idea. It doesn't have to be real, but it's still an idea. So this would be written as a formula, but if I write this as a statement in this case, by enclosing it in pair of brackets, then for Sophia, this is no longer just an idea of an alien, then Sophia will assume that I know a specific alien and I'm talking about that specific alien in that very moment. Okay. Does anyone want to ask any question about this differentiation between formulas and statements? If you don't have a question, maybe you want to...
Zurab, I see Eric is raising his hand. Eric, please, you're welcome to unmute yourself and ask your question.
Thank you so much. I think I'm still a bit lost about the idea of a formula in the statement. For instance, what you have on your board right now, there are two sort of expressions. Which one is the statement? Which one is the formula there?
So here, the top one is a statement.
Right.
The bottom one is a formula. And the top one is a statement because it fits this pattern.
Right.
In this case, the pattern is just very simple. In this case, it's just this, right? Where the three dots are this alien.
All right.
And the bottom one is a formula because it does not fit that pattern.
But to me, it will fit that pattern because you can actually put two square brackets on either side.
Well, if you put square brackets, then you have changed your expression.
Okay.
If you take this and you put brackets around it, then you've changed your expression. Now you're not you now go back to that. Sophia will be reading us literally, like in any programming language. Every character matters. Or maybe I misunderstood your comment. So how does this fit that pattern? How does this fit that pattern? Can you please explain one more time?
Because I'm just thinking it fits in that pattern because you're saying you put a square bracket and some statement in between. Mm-hmm. So here and in the second one, if I put square bracket on either side, alien becomes the statement in between.
No, but if you do that, so these square brackets must be already part of what you have written down.
Oh, okay, all right, okay.
Yeah, sorry, yeah, thanks for that question.
Okay.
So when I say that it must be of this form, it means that not that I can modify it to be of that form, but rather than it already needs to have that form.
Thanks. I get it now.
Okay, great. Thank you very much for that question. Yeah, thanks, Joshua. You also explained that. Thank you. Okay, are there any other questions about the difference between formulas and statements?
There are two hands up, Zurab, from
I'm sorry, I keep missing those hands. Sorry.
And from Belishra.
Yes,
please. Yeah, please, you're welcome to unmute yourself and ask your question.
Yes.
Thank you. Yes, please.
Okay. The question is the difference between the statement and the formula. Is it because with the formula I can do mathematical operations on, or okay, I don't know how to ask this, but yeah, what's the difference between the formula and the statement beside the writing? Like, does it mean if I have a formula, I can do mathematical calculations, but if I have a statement, I cannot do anything with it beside it being a statement?
We will come to mathematical calculations in a moment. At this stage, and that's going to stay on forever, the difference is in how I interpret what you say. Do I interpret it as a claim that you're making, or do I interpret it as some idea you want to consider? For example, let's take some real life example of this. Imagine I told you, I want to go to Mars. Okay. Or maybe I say, I'm going to Mars. So let's put it like this. Imagine I say, I'm going to Mars. Obviously, I can't be, literally, it can't be true, right? We don't have technology yet for someone like me to go to Mars. So I'm probably just like considering the idea that maybe I would like to go to Mars or something like that. Huh? Now, compare that with the statement, I like to eat, I enjoy eating ice cream. So when I say I enjoy eating ice cream, that probably means that I really like to eat ice cream, right? I'm probably stating a fact. So if I'm stating a fact, I would write that thing as a statement. But if I'm just considering a possibility or just considering a thought, I would want to write it as formula. Does that make sense? Does that answer your question?
Yes, it's because I was thinking it in terms of, say I have, maybe let's just say I'm doing an if loop and I'm like, if x is equals to 0, since that's like something like a statement, do I have to now use the brackets to show that this is a statement, not a formula?
Yeah, so how we're going to use Sophia statements and formulas, Sophia formulas to encode mathematical computational expressions, that's still to come.
Okay.
At this point, all we want to understand is that when I wish to state a fact and I want to kind of claim that that fact must be true, then I will be using the statements for that. And when I don't wish to do that, when I just want to consider ideas without being kind of confined to truthfulness of those ideas, then I will be using formulas. Does that make sense?
Yes.
Mm-hmm. So that's where we are at this point. But you will soon see how these two will then be used to construct the actual mathematical, the familiar mathematical things. I don't want to call them any of the words now because we reserve these words for the Sophia terminology. And there was another question from Tembelihele.
That was me.
Oh, sorry. Okay, maybe then it's from Zisipo.
Hi.
Hi.
I just wanted to find out. So the square bracket, alien square bracket is a statement, right? And then below it, we have alien, which is a formula. Now, if below we had like empty square brackets, that would be like a formula as well. Like below that alien, you have an empty square bracket that will be like formula. No word inside.
This.
That's empty, yes.
This would still be, no, this would be a statement.
So that would be a statement.
Yeah, because it fits this pattern where the contents is still so empty expression is still an expression. It's not a statement, but still an expression. So it fits this. Okay. So the rule was that here we need to have expressions like what we explained here. So this inside part must be expressions, but they can also be empty. Oh, because empty strings are expressions.
Okay. And then if we had now the alien word outside the empty square brackets, that would be?
This would still be this would then be a formula.
Oh, all right.
Because it doesn't have this pattern where you have blocks of enclosed brackets.
Okay, thank you.
So you can experiment with this code that I showed here, the code for testing something, whether something is a statement or not, and also for the expression. If you at some point feel that you're still uncertain about this, you can experiment with that code and see and confirm for yourself whether something is a statement or not. And that's the beauty of the Sophia module, that now we can use it as a tool for learning mathematics, right? Asking questions to Sophia and getting answers, and this way refining our knowledge of concepts. Okay, let's move on. Sorry, I'm sometimes lost with my windows here. Now, the next topic, and this will be the last topic for today's session, is this concept of ontology. We want to take Sophia expressions and break them down in terms of how they're composed and look at each layer and classify each layer as a statement or a formula. So here we have a good example. we begin with the top line in this picture. So you see in the top line, we have an open bracket, and then it closes, and then we have equality in the middle, and we are equating 2 plus 2 with 1 plus 3, right? At this point, because we don't have brackets around number 2 and number 1 and number 3, at this point, Sophia doesn't really know what we mean by 2 plus 2. For her, it's just like an expression. It would be, it could have been apple instead of 2 plus 2. But that doesn't matter. We don't worry about the meaning for now. We just want to understand the structure of Sophia expressions and statements and formulas and so on. Now, if you think about this, you can take this thing and then you can take off the outer brackets, right? When you take off the outer brackets, you'll end up with a formula. Yeah. But then you can isolate those blocks with enclosed brackets, which will be statements. And so if you think about this way, so look at the second line. If the equality sign wasn't there, this thing would have been a statement. But the equality sign is there, so I erase it. But then still, because those things were kind of separated by equality sign, I want to keep them separate. So I end up having 2 statements there. And then I could take off the outer brackets again, and then I end up with formulas. So you begin with any kind of Sophia expression, and by this process of taking away the brackets, you alternate between layers where you have statements, formulas, then statements, then formulas, and so on. So you have this constant exchange of ideas, which are formulas, then stating them, and then forming new ideas out of them, and then stating them. It corresponds to how in life, how science works. We come up with hypotheses, then we experiment, and using the results of experiment, we form new hypotheses. And so this kind of cyclic process of combining the abstraction and the concretization, if you like, is very much engraved into the structure of every single Sophia expression. So let's work out the ontology for a specific example. And one more thing to mention, that this intermediate processes of combining something into the next layer is called synapses. Okay, so let's work out an example now, which is different from the one that was given earlier. But I'm going to now go backwards. I'm going to start with a few components that I would want to join and so on. Let's say we start with x equals 5, and maybe we actually start with x 5, x 7. So on their own, each of these are formulas, right? Because of what we discussed before. We can now do synapses to them, and there are many ways of doing it. It means basically turning them into statements. I want to group these two together by first, before grouping them together, I want to first turn them into statements just by putting single brackets around them. So this would be an example. Each of these arrows would be an example of a synapsis where out of formulas, we obtained a statement. We now have many statements, right? And then I want to now do the next step. I want to take these statements and create formulas out of these. And I'm going to do it separately. So I want to group these two together and those two together. But the way I'm going to turn them into formulas, I can't just write this, because then this wouldn't be a formula. This would be a statement. I want to insert some other characters between those blocks. And specifically, I want to insert equality there. Actually, I changed my mind. Sorry. I want to insert not equality, but inequality. So I want to say x is bigger than 5. And here I want to say x is less than 7. now as a result, I have formulas. And I want now to do one last step where I will join these two formulas into a single statement. And that means putting brackets around each and then just placing them next to each other. So this becomes a statement. Now, the interesting part here is that if I started off from here, right? This decomposition, this tree we get here would have been forced. I mean, there's no other way to decompose this. I could have gone many different ways starting from this layer. I could have joined these things in many different ways. But when I finish, if I want to recover back what I had, I can, and it will be uniquely recovered back. So this is how it kind of gives you a little bit of insight into Sophia expressions, knowing that, well, first of all, any kind of Sophia expression will be either a statement or a formula, basically by definition. But then moreover, we can take a Sophia expression and decompose it into other expressions and then further decompose them and so on. But these decompositions are such that every time we move to the next layer, every time we go down, right, we alternate between having statements and formulas. And that's what makes the whole process unique. You know? This feature of Sophia expressions will be basically the means for encoding logic into a Sophia expression. This thing is called ontology. And it is thanks to ontology that it will be possible to turn every single Sophia expression into something logical. So Sophia might not know what you want to talk about when you talk to her, but she's a master of logic. So whatever you will tell her, she will kind of do this to that. She will do the ontology to it. She will decompose your initial starting point into a tree like this. And from that, she will be able to extract the logical information in your expression. Okay. Now, exactly how this will work, we will see later on. But for now, the idea is for us to kind of understand this concept of ontology. I see that there are probably some questions there. Let's check. Yes, we are going to be finishing at 3:30. Thank you, Francesco. So I'll just take a few questions about ontology and then we'll be done. Yes, Pumelelo.
Okay, thank you very much, Professor. I want to ask, maybe as a rule of thumb, should we say that statements are formed by square brackets and formulas are formed by introducing mathematical operators?
Yeah, except that these operators don't have to be operators always. They can also be letters, words, whatever, things that are not enclosed in square brackets. But yeah, that's a very good, it's a very way of thinking about it. Very good way of thinking about it. One of the activities here asks you to build your own Sophia expressions and then present their syntactic ontology. And I think there is also an activity on Moodle that asks you to do that. It's this activity. Come up with your own Sophia expression and draw its ontology. And then on that drawing, you must mark all statements and all formulas like we have done here. And then take a picture of that. And I'm going to be going through each of your submission and giving you some feedback on that. Okay, so let's test out whether this concept was clear or not. Let's go the other way around now. Let's begin with some expression. This time I'm going to begin with a formula. So let's say we have A equals B and B equals C. If I want to describe the ontology of this, in this case, this is a formula, right? Of this formula, what would be my next layer? So how would I decompose this? I can give you a hint. It will decompose into two statements, and maybe you can write what these two statements will be separately. So what goes here and what goes here? This must be some statements that together in a synapses combine into that formula upstairs. Heinrich wrote A in brackets equals B in brackets, and separately the other one. But so that's almost correct. The only problem with it is that we want the actual statements. So we don't want to skip a step. We first want to keep them as statements. So we want to keep those outer brackets as well. That's right, Donald. And then in the next layer, we will take off those brackets. So then they become formulas. And what about the layer after? So now we have a formula. So we want to decompose it into statements, right? Exactly. So that will be one statement, and the other one will be B. And here we will have B and C. And then we take off brackets again. We'll get A, B, B, C. So we had previously statements. And then at the end, we end up with formulas. Great. Thank you for your participation with the chat. I think we can start concluding this lecture. If anyone has any questions you would like to ask, please go ahead. Otherwise, I don't have anything more to explain. Yes, Joshua?
I have a question about Sophia. The answer to it might just be for me to go a little bit further into the work, but is there a level at which Sophia understands any arithmetic or these statements, or is these just kind of like element-wise ontological, like our thing? You know, how do these statements deconstruct in order for you to say that something is true?
Yes.
Is there some arithmetic to it?
Exactly. Sophia can understand everything in mathematics, including arithmetic, and any part of science as well. Anything that's logically precise, it's possible to express in Sophia. So it's a very powerful language. It's not the only such language. There are other mathematical languages which are like that, but it's the simplest one in the sense that I explained to you in like basically 1.5 hours how the syntax of the language works. Whereas other languages, we would have to spend maybe a few lectures for you to understand the syntax. But it's all-encompassing language. Anything that's formal can be expressed in Sophia. Does that answer your question, Joshua?
Yes, it does. So just like a follow-up question, kind of fun. Can Sophia generate? I know there's this whole like 700-page proof that one 1 + 1 = 2. Can Sophia, if you start with the right ingredients, can Sophia generate that formal logic for you?
Yeah, it doesn't take 700 pages for that. It's very quick. On the GitHub page, there is an example file. And I think either it's proved there or you can use those to easily construct the proof. I have not included that in this course, but I could easily explain in 1 hour how to get there, how to get to the proof that 1 + 1 = 2 or 2 + 2 = 4. So we don't need that many pages.
Okay, thanks.
Haneli.
Hi, so we are actually working as a group here at the Northwest University, and we are working on university PCs that are in Linux, and I don't understand what our system admin did specifically to the machines, but Sophia, when working through the activities, one of it cries about not being able to concatenate a string and an instance. Do you know if there's...
Yeah, this problem was pointed out to me on WhatsApp. I don't know how to solve it because I don't understand Linux that well. I think what I could advise maybe is to use online Python interpreter.
Yeah, we have tried it, and if we do use some online stuff, it works, and if we use some stuff that is installed using Anaconda, it does work. So I was just wondering if maybe you had an idea of what type of weird thing our system admin may have done or something like that.
No, I'm sorry, I don't have an idea on that. I'm not that well computer literate. I actually never worked in Linux as well, but maybe this is something we can talk with Benjamin, and maybe he will be able to help us figure out the source of that.
I would also suggest to get in touch with your system administrators and ask them to sort it out.
Yeah.
Good suggestion, yes.
Okay, thank you.
Sorry, I can't help.
Because
there.
you might not be allowed to Benjamin is recommending to upgrade Python. Maybe you're not allowed to do it on those machines because of some permission issues or things like that.
This Sophia module should not require necessarily an upgrade. So yeah, so there's some issue with strings, and I have no idea what it could be. The character encoding as well. I don't know, but yeah, I really don't know.
Okay, thank you.
Thank you, Anneli. Thank you. Thank you to the whole group for
thank you, Prof. Actually, I want to ask about the general nature of using computers to prove statements. I remember in graph theory when they proved the 4-color theorem. At first, a lot of mathematicians met the whole proof or the method with skepticism. So I would like to ask, how far is the sentiment towards using computers in order to establish proofs and the truth of mathematical statements?
Yeah, so the thing is that the proof assistant produces a proof for you, right? But then you want to go through the proof. And if the proof is just checking different cases, which is what happens in the 4-color problem, it just checks like many different cases. It's impossible. It becomes virtually impossible to go through it by yourself. Yeah. I mean, it's similar to, let's say, believing Andrew Wiles that he proved Fermat's last theorem. I mean, we have to check his proof, right? We cannot just believe him. And in fact, in the beginning, when the proof was checked, a mistake was found, and then he was able to fix the mistake after a year. So relying on a computer-assisted proof is similar to relying on a proof of a mathematician who has produced several volumes of proof. You still have to check, other people still have to check. And if it's a computer, it could be not 3 volumes, but 1,000,000 volumes. And then checking, it becomes more difficult. So computer is not less reliable than a human being in that sense. It's just that because computer can produce so much information, we still need to check the proofs, even if it's produced by human. And that takes a long time if the proof is long. I think there is, did I answer? Are you happy with that answer, Mpumelelo?
Yes, thank you.
Okay, I think we don't have any more questions, right? So I hand it over to you, Francesco.
Yeah, Zurab, thank you very much for a very nice introduction to Sophia. That was really great. I enjoyed it very much. And from the reactions and the many questions and comments, I have the feeling that everybody welcomed your lecture and enjoyed it a lot. So we are looking forward to see how this story evolves. Yeah. And I think I will remind briefly everybody that your next lecture is on Wednesday afternoon. Yeah. So, but our participants should be online mornings and afternoon. So tomorrow morning they will. We have the beginning of another course on machine learning for bioacoustics. Yeah. And we will start again at 9 o'clock tomorrow morning, like today, and like we will do for the rest of the next 2 weeks. Yeah. So Zurab, thank you so much for preparing so nicely your lectures, Moodle, the quizzes, all the materials, the blog. Yeah, that's really phenomenal. Yeah. So thank you so much on behalf of everyone. Yeah. And as soon as possible, we will upload the video on our YouTube channel so that some of you who might have missed it now have the opportunity to watch it again, maybe this evening or tomorrow latest. Perfect. So thank you very much, everyone. Have a good rest of the week. And if you are interested in gravitational waves, at 5 o'clock, we have an excellent talk based on computational methods. I'm not sure whether they use Python or not, but we will find out. So if you come, that's a question that you can ask the speaker. Yeah? So thank you very much, everyone. I hope to see some of you later at 5. And otherwise, I will see you tomorrow morning. Yeah. Thank you, Zurab. Thank you very much.
Bye. Thank you. I'm happy to interact with whoever wants to through WhatsApp and Slack and so on. So feel free to write to me if you have any questions. Bye, everyone.
Thank you. Bye. 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 All the best.